This Tic-Tac-Toe project was created at Cal Poly San Luis Obispo for the class ME507 Mechanical Control Systems Design. In this video, I'll be first showing an operations demonstration of me playing Tic-Tac-Toe against the robot. I'll also have some of the software running on the screen so that you can see how the robot sees the Tic-Tac-Toe board and how it chooses to respond to it. I'll then jump into a hardware overview showing the individual components and boards. I'll then talk about the interconnects, connecting together the custom circuit board, the actuators, the MATLAB program, and the rest of the system. Next, I'll go into a MATLAB state layout and code, looking at how the major program works. I'll talk about the MinMax algorithm that's used to make the playing decisions. I will then talk about how the markers are delineated, how it tells the difference between X's, O's, and nothing. We'll then take a quick look at the CAD model before jumping into the C++ state layout that runs on the custom board, before looking at the Eagle layout, and then another quick look at failure modes.
Okay, so taking a look at this, let's press button to start. You'll notice that we see place move, or press button to have robot move because it detects nothing. In this case, we will have the robot move first, so I'll press enter here. It will have to think for a while because it's working through all the individual child boards. You'll notice it places an X. The robot has been programmed to do X's if it can, just because O's take forever to draw. So I'll place an O here. And detect that as an O. O's are 2's, X's are 1's. So in this case, it looks like it's going for a play across the top. So I'm going to attempt to block it. Just for row 2, column 2. I will have to block again, but in this particular case, I actually cannot block both of them. So I am going to play right here. And it knows that winning is more important than blocking me, so even though it could have blocked me in that particular case, it opted not to. You'll notice it knows that the robot has won, so let's play another game. In this case, it knows it's trying to start another game. The board is not clear, so I will have to clear the board. Okay, board should be clear. Let's try this again. And it knows. So in this case, I am going to play first, and I am going to play as O's again, just for speed. Oh, right there. Because I played first, there was a lot less potential child boards, so the pause time at the beginning when it's computing the best move to make was a lot shorter that time. I am going to... let's play here. And it blocked it. I'm gonna keep it on the defensive here. Maybe you can say defensive with Tic-Tac-Toe. Place here. Hopefully it'll pick that up. Drew it kind of close. And it did. Locked again, so we're going to have perfect symmetry here. It will always allow you to play out a cat's game. Knows that the cat is won, press the button to start.
Here is a closer look at the mechanics of the system. The entire system was designed in SolidWorks for the mechanical components and Eagle for the custom PCB before being fabricated. Some other additions such as the camera holder and the power supply on this far side were added after the fact in order to make it slightly more compact and require only one power supply. So starting down from the bottom, first we have this 3D printed little rack and pinion system. It's currently in brake mode, so I can't turn it by hand, but there is a small 3D printed pinion attached to this servo here, and a rack on a EXPO marker holder. And what this allows it to do is move up and down and creates the 0.5 axis of the plotter. There are two NEMA stepper motors, one located over here, one located over here, that permit the carriage, which is located in the very center, to move in the X and the Y direction. This is something called an H drive, which basically allows you to locate your motors outside of being mounted on one of the axes and makes it lighter and more stable in general. However, it does require you to have a much longer belt run. In this case, this wasn't much of a concern as the belt was inexpensive, and for an application that doesn't require a lot of torque, we had no danger of it stretching. Moving up a little bit further, this is a whiteboard which was actually cut out of one of the old whiteboards I got my first semester of college. Nothing special. Electrical tape is used to create the Tic-Tac-Toe board. Moving up a little bit further, there is the custom PCB we'll take a look at in more detail later, but this PCB essentially has the input, the I/O, input and output, for most of the functionality on this project. In terms of output, it has a header pins to connect to the servo. It has a UART port to connect to the MATLAB interface. It has the stepper motor ports right here and right here to control the two stepper motors. It has obviously the power in right here, and then finally a PDI port for programming via Atmel Studio, and our voltage input right there. In terms of the rest of the mechanics are relatively simple. They were designed to be laser cut. So right here, this is simple plywood that I bought from Home Depot. This is also plywood, and these ball bearing sliders were actually available in the lab. Thank you, lab instructor, who they were left over from older projects, but they are available very cheaply on Amazon, though if you are to get them, I highly recommend to check each one for the quality of the ball bearings, as those seem to vary substantially. The pulleys that you see located here and the belt were either bought straight off of Amazon. I believe this is 3mm wide GT2 2mm pitch belt. I can check on that. The last components over here, moving further up, there is a power supply that is set to take 24 volts. Let me change camera angle real quick. So 24 volts directly in from the power supply. There's a, you can't see it, a soldered Y connector that directs the 24 volts directly into the motor controller side of the board. And there is an internal DC-DC converter in here that steps the 24 volts down to 5 volts for the microcontroller. This microcontroller is an ATmega256A3BU. Something that powerful is not necessary for this project, but we were originally intending on using far more timer counter channels than we ended up using. If I move up a little bit more, you can also see the camera. This camera is extremely old. It was my first ever webcam that I ever have, I believe. I think it only runs at 480p, but in this case it is sufficient to detect the different markings on the board. So here is a better video of some of these interconnects. You'll see the header pins that we use to connect the servo over here simply plug directly into the circuit board. You will see our UART header pins over here. Those actually connect up to this extremely cheap prolific knockoff that I got years and years ago into the computer running MATLAB, which itself is connected over simple USB to this old Logitech webcam that I also got years and years ago. And also here you'll see our PDI port, which is connected to our programmer right here. This itself is actually running in debug mode at the moment. Everything was developed on my laptop, and we run everything in Atmel Studio. We'll talk a little bit more about that software development later.
There are many different communication protocols that we use for this project. The most obvious of which is USB, where we have our Logitech webcam connected directly to a PC and communicating with the MATLAB script. This is how we get the raw image. The way that the MATLAB script, which alternatively could be run on a Raspberry Pi as an executable, is via this UART USB adapter. Is actually a prolific PL2303 knockoff that I got years and years ago that will essentially convert this into a UART package that the Microchip ATxmega256A3BU can read. And this microcontroller was far more complex than what we needed. We were originally going to use a lot of encoders to measure the position, but we actually switched to stepper motors instead, so we didn't need all those extra timer channels. But the way that the microcontroller communicates with the two individual stepper drivers is actually via SPI. And essentially the way that we've done it is we have two individual chip selects that select which of the stepper motor drivers is listening at any given time, and a shared MISO, MOSI, and clock line. The final interconnect is the motor leads that are simply the multicolored wires that you see connecting to the two actuators, which are the steppers. Not included here is the servo itself, which is actually connected directly up to the 3.3 volt power supply. It's supposedly supposed to run on 5 volts, but it seems to operate for our purposes on 3.3 volts just fine. Here is a state diagram of the top-level MATLAB program that determines what state the program will move into at any particular other state, and also describes the transitions between the states. This is relatively simple, as the large outer loop always cascade into each other. However, the area where different paths can be taken is at the check one state, where essentially we can switch between the turn being the human and the turn being the robot, and depending on the one condition can actually transition back to start game. Start game itself will not initiate, or sorry, will not transition into another turn until the board is clear, and will self-transition back into its own state if this is not the case. So now I'd like to take a little bit closer look at the software. The MATLAB Code is one side of the software that makes it run. We also have a C++ project that's running on the microcontroller itself that actually operates the motors and some of the other lower level stuff, but this is the high level determination of the best play to make and instructions sent to the microcontroller. So this main script does most of the controlling here. The way that it is set up is it actually enumerates each of these slots as characters in a cell array to store the potential plays in. The way that it communicates with the microcontroller is via UART. And it does that over a very typical serial communication interface. This is accessible straight through MATLAB. In this particular case, I have it on COM5, but you could also have it search for it if desired. We've set up a terminator to show what is the end of a UART package. You set up the camera on Windows. I believe you can just load it in using the webcam command. It might be different on Linux. Now, getting a little bit deeper into the way that the program actually operates, it will first start by calling a series of helper functions, such as crop image and classify image, that will essentially just crop the image into a specified number of rows and columns, and then classify it. And we'll talk about the classification algorithm a little bit more later, but what it will essentially do is it will assign a number to each of the 9 slots. So it will assign a 1 for an X, a 2 for an O, a 0 if it is blank. Next, we get into the repeating portion of the program. Basically, if there's any room, it will continue to repeat. If not, it will exit and go into anything that is not the first move. So this is simply the first part of the program when the first move is made, and is very similar to the execution in the subsequent moves, which I will look at now. So after taking the snapshot, cropping the image, and classifying it, it will then use this program called determine best move, where it will try to find the maximum value that the robot assigned to each potential permutation of the board. Now, the way that this works is it's iterative. Basically, determine next move, which we can look at right now. And it implements the MinMax algorithm. Actually, I need to tell it real fast. Determine next move is itself relatively simple, where it will simply iterate through all the rows and all the columns and create a child board for each potential child configuration. It will then determine if we are minimizing on our turns or maximizing on our turns and minimizing on opponents' turns, and it will assign a value of either 1 if the player won, 0 if the cat won, or -1 if the other player won. So in this particular case, it will actually go back through and recursively call itself. So determine best move is calling determine best move and switching the min-max flag every single time, so that it will permutate down until there are no more moves available and it has reached a terminal state of the board. It will then place an assignment and propagate that result back up. So minimum and maximum, it's called a min-max algorithm. There are ways to make this much, much simpler using the symmetries of the board, or simply computing the minimum maximum one time and storing that in memory. But for an exercise in this algorithm, it actually calculates it every single time. So after determining the best move back in our top level program, it will it will display this to the user in terms of playing in best row and the best column, and it will write that move to the UART serial terminal, where it will write out a $sign to indicate the start of the package, and then the appropriate string of characters. Then we wait until we get a done reply from the microcontroller and swap the move over to the human if it was the robot's turn, or the robot if it was the human's turn. At that point, it's relatively simple. We just check for a terminal state at every point. If we hit a terminal state, we can determine if the cat, the robot, or the human won, and then we can repeat after checking if the board is clear. And I will talk more about the min-max algorithm a little bit later. So to elucidate the MinMax algorithm a little bit better, I have created this little graphic that demonstrates just one propagation of the algorithm. So we start with a parent board, which in this case has 6 plays and 3 empty slots. The first step, assuming that is the robot's move, is to maximize. So it will place an X in each of the 3 empty slots, assuming that is its symbol. So in this case, you will see that placing the X in the lower right-hand slot creates a win, which the robot will assign a +1 value. However, the other 2 slots result in neither a win nor a lose, and it will then go to the human's turn. So in this case, it is desired to minimize. In the far left-hand side case, minimization would show that placing an O would result in a loss for the robot, a win for a human, which is assigned a -1 value. Or alternatively, if the O is placed on the far right-hand side, then we are eventually going to see a tie, a cat's game in this particular case. Over here on the right, we also see one possible way for the robot to win would be if the human did not block and the robot was available to place another X, so that is assigned a +1, and finally another cat's game on the far right-hand side. You'll notice that we're actually missing a step here, but we know that the ultimate value we're going to be getting is either a +1, a 0, or a 0. So what the robot does, it will then propagate this upward, so the +1 will then become propagated up to the next level. However, this is a minimized level, causing the -1 and not the +1 to be propagated upward. However, now we're on a maximized level with -1 over here and +1 over here. In this case, the +1 is maximized because it's the maximum value, and the robot will immediately choose this terminal state on the right-hand side where it will win and be assigned a +1 value. Next, I'd like to talk a little bit about the way that the image classification works. So MATLAB is extremely powerful and has a lot of built-in image processing tools that will essentially allow you to accomplish this with very little code knowledge on your own part, which was good for me. So starting here at image 1, the raw image, you can see there are several errors. The O is left open at the top. There are several little marks on the whiteboard. The first thing that the robot does is it will grayscale the image, turn it into only a grayscale, remove the RGB aspect. It will then move it into a binary image using a threshold, where you can see it will assign either 1s or 0s. In this case, it's a flipped binary image. It will then invert that to a binary image where we assign our 1s in white to all the areas that were seen as dark. It will then remove small aberrations from the image of under a certain size. That gets rid of all the little markings. It will then create a small morphological element to close in gaps of less than a certain size. And if you remember back to when this processes the X's, what this will also do is it will cause the narrow portion toward the center of the X to become slightly more boxy, but the big benefit is that it will close out any O's that are not fully closed, and will then allow it to fill in the gaps. And here is our final image down at the bottom. And like I said, the benefit of MATLAB is it allows us to do this extremely simply, so we can accomplish this in just a few lines of code. The first RGB to gray line converts us into a grayscale image. The second image uses the mbinarize function, which allows you to set the foreground and background polarities. mComplement essentially just flips all the 1s to 0s and vice versa. Our BW area open function allows you to specify the size of the aberration to remove. This strel function allows you to create a morphological structuring element of a specified size. If you increase the size, this will allow you to cover in larger gaps. And then finally, mclose will allow you to fill in the small gaps, and mfill allows you to fill up the whole openings. And what this final line here allows us to do is essentially assign the filled image into a cell array for later analysis. Here we can take a closer look at the CAD model for the system itself. We laid everything else out in CAD first before fabricating it, just to make sure that all the design and geometry was correct, so that we need to redo as few parts as possible. Here you can see in a little bit more detail the way that the H drive is set up. We have our two bearings over on this side. Those are on either side of the carriage. Our front view, you can take a look and see the other axis running on the side. In this case, we only have two bearings in total because we have a much, much smaller secondary carriage. And here's a better detail of the way that the rack and pinion slide is set up. The pen setup is 3D printed of 4 individual parts. The pinion, mount, rack, and pen holder, and it is all powered by a SG90 servo. It is held together via super glue and small screws. The pen itself is removable. This small 3D printed portion simply deforms enough to allow the pen to snap in and out, and holds it tightly enough to draw effectively. Next, I'd like to take a closer look at the program that runs on the microcontroller. So here is the task diagram. It is extremely simple. There are only 2 tasks, task communicate and task motor. Task communicate runs at a slightly tighter timing of 1 millisecond, while task motor runs at 10 milliseconds, just because the motors themselves do not need to be updated as quickly. There are 3 shares that are used to implement communication between these tasks. These shares are enabled through FreeRTOS, the ME507 port of it. The 3 shares are as follows: a cell pointer, a XRO pointer, or a send data pointer, that do just about what they sound like. The cell pointer indicates what cell to play in, the XRO pointer indicates which character to play, and the send data point is a simple flag that tells the microcontroller when to communicate back to the UART port to indicate that it is done making its move. Now, moving down to the state diagram, we will see here that we will move always from the initialized state into the idle state for the communication task, where depending on whether or not we get something, we will either transition to the send data state, or if it is time to communicate that we are done with a move, we will send the done over serial. If it is time for us to make a move, we will check for characters from the UART port, move into the interpretation state, where we'll check for the $sign to indicate that the package is begun, where we will then move into the XRO state to interpret which one to play, and then the get index state, where we interpret where to play before transitioning back to idle. Very simple. The other task, the motor task, transitions always from initialize into the idle motor task, and will always move from idle into moving, because we assume that in the idle state it starts in its home, which is the back left of the board when looking straight onto it. Essentially, if the cell pointer is less than 9, because the cells are enumerated 0 through 8, it will then move into the moving state, where it will then transition alternatively into the cross or the circle, depending on the pointer, the memory location that the pointer points to, whether it contains the X or the O designator as 1 or 2. It will then set the index appropriately and move home. The home state, in this particular case, we are calling 99, where we will store the 99 into the memory location pointed to by cell pointer to indicate that we are back where we started and are ready to go back into the idle state.
Okay, so jumping now into a little bit of the code that runs the microcontroller. Again, I am not a software engineer by any means, and this is quite messy. And a lot of it was developed by my professor and lab instructor at Cal Poly. So, like I mentioned earlier, we have two different tasks. We have a bunch of different functionality hidden in different files here. The tasks aren't exactly named very intelligently here, as we thought we'd need different tasks for two different motors, but we eventually consolidated them all into a single task motor A file here. So essentially, what the main task does is it sets everything up, makes sure that all of our ports are set correctly, initiates our individual pointers. Here are the 3 pointers we talked about earlier, sets up the internal oscillators correctly, in this case at 32 megahertz. If I remember correctly, sets up our serial port, on this case USART F0 we configured, sets up our two different tasks, in this case our motor task and our communicate task, and the individual priorities that they run at. In this case, the priorities are exactly the same, and I think we might have the timing set incorrectly here, but in general, it's tight enough that it works just fine. Finally, we set our individual ports as the correct outputs and inputs, and we start our task scheduler. So to get into the real meat of our individual tasks, let's take a look at the communication one first. So essentially what this task does is it will take a look at the received information over USART, and it will then put the determined character and move into the memory locations pointed to by the individual pointers we discussed earlier. So in our switch state, we go through our initialize into idle, where it's checking to see if we got anything at all. If it does, we transition into our interpret state. And interpretation here, we check for our $ ASCII chunk here, which represents the start of the task, which will allow us to go to the get X or O task. In other cases, we didn't see it, so we're going to transition directly back to our idle task because it was not a valid package that we received. In X or O, we're simply checking which of the two that we got, and we then go into get index, where we check to see what the index sent over USART was. And we store these into the memory locations pointed to by the X or O or index pointers. If, however, we are done with the move, which is indicated by the send data pointer, we will then send out the done string over the USART port and transition back into idle. So relatively simple. Slightly more complicated is our motor task. Again, this is called task A, but it really handles both motors. And I'm going to skip over most of this, but the highlights essentially are we have our X cell positions, and our Y cell positions, which are essentially just lookup tables that the program uses to determine which motor positions correspond to an XY position. And it is important to remember that if you take a look at the system dynamics, that this is a one-to-one correspondence between the XY positions and the two motor theta positions. It might not be easy to see just intuitively, but if you take a look at the math that we looked at earlier, it will always work out to a one-to-one correspondence. Next, we're basically setting up the auto driver. This auto driver was adapted from a SparkFun auto driver that used the same chipset, but permitted Arduino. The porting process was relatively simple, mainly with changing some of the syntax around and making sure it worked with the SPI program that runs on this individual microcontroller and not the Arduino microcontroller, which I believe are generally ATmegas. In here we're running XMega. So moving on a little bit further, you can take a look at our initialized state. Basically just sets everything up like we talked about earlier. But the important part is where it generates the motor position lookup tables. These are in the AROT-VEC and BROT-VEC, where essentially it will use those two, where it will use that matrix we took a look at earlier to transform this scalar using scalar and then the cosine and sine values of the theta values to come up with a lookup table for each of the individual positions that we have up here. So this will be computed every time. It would be more efficient to do it once beforehand and not compute it every single program, but this allows us to easily change if for some reason we are not drawing in the correct location on the board. So it then goes into more setups where it essentially resets the two chips. It will set up all the different configurations for motor A and motor B, such as the acceleration, deceleration, the PWM frequency. This is actually surprisingly important because the PWM frequency created a very annoying sound that my lab instructor did not like at all if it's set to the wrong frequency, but is relatively silent at 31.25 kilohertz. The other significant part here is the hold kval. So essentially, this is the current that the power supply will try to deliver to the motor at stall. It's kind of hilarious because if this is set too high, the motor can pull way more current at stall than it does at full speed and heat up the motor driver board to motor driver chip to ridiculous heats, and it's quite painful if you touch it. Lifts up the servo, and then we transition into idle. So essentially, we check for the cell location from the cell task and transition into a moving state. In the moving state, we will use our transform scalars to look up the X and Y cell positions and transform them into an offset. The offset will tell us where to go based on what we received. And then we will tell the board to go to offset A and B. Essentially, this will just go until the board A and board B, which correspond to the two motors, are not busy, in which case we'll transition alternatively into a cross or a circle. So the cross and the circle are slightly different. The circle is actually not a circle, it is a many-sided polygon, where I believe it's a 70-sided polygon, where essentially we will loop through an index going up to 70, where we will have individual little offsets that will tell us to go to each of the individual vertices that make up the polygon. It is slow. Eventually, I would like to change it to simply draw a smooth circle by changing the direction but not the magnitude of the velocity vector, but we didn't actually have time to implement that properly. And what you'll notice here is it will actually wait until do a busy check on both of the boards to see if they actually got to each vertex before moving on to the next vertex by incrementing the index variable here. And you should also notice that, again, we are using the offsets and the vector indices that we created later to get us to the proper location. The cross, on the other hand, is much simpler. It simply has a couple of steps to draw the straight lines and move the pen up and down at the right time. Simple, so I'll skip over that. Finally, we move home, which we've set as 0 and 0, very simple. And like I mentioned earlier, we put a 99 into the memory location pointed to by the cell pointer to show that we are back at home and back in our idle state. And that is the most of it. Some junk code down here that we never ended up cleaning up.
So, taking a closer look at the microcontroller and the board design, the entire board was laid out in Eagle. I'd like to thank my lab partner for handling a bunch of the difficult aspects of this. I am not an electrical engineer, so some of the quality that you will see here is not as great as some of my colleagues. So relatively simple setup. We basically have our power supply, which gives power from the 24 volts, which had been already stepped down to 15, down into the 3.3 volts that the microcontroller runs at. We have our analog and digital portions of the controller set up, so our AVCC here, and its own decoupling capacitors located close to the appropriate pins, separated by our bead, and our inductor down here, and of course our individual decoupling capacitors on our VCC side. We have some unused limit switch connectors. We were going to use those for zeroing the axes, but didn't find those necessary. A couple of servo pins connected directly to the PWM signals and the same VCC output. And then our reset switch, which was actually never soldered, and our UART port. Moving on to microcontroller page, it's relatively simple. We have our external 16 megahertz external crystal oscillator over here, and all the individual vias that we connected to almost every single port on the microcontroller, just in case we needed to use them later. The only real notable portion about this is we had initially accidentally connected one of our VCCs to ground. I don't know, I think we might have fixed it on this revision. Not recommended. We actually had to pull it up off of the pad and just kind of leave it hanging there, but thankfully for us it ended up working out. Not very easy to change after your board is fabricated. Then finally, moving on to our motor driver page, that should be titled Motor Driver. We have two extremely similar motor drivers because they're using the same chips. It's a relatively simple setup, not much noticeable. We have our large and small caps that you see. You can see those most visibly on the board over there. Our regulated voltage divider here, because we're running it at 24 volts. Our four individual pulls of outputs at the four corners of the microcontroller. And also our flag and busy pins. Flag isn't super important for what we're trying to do, but busy is. We actually are frequently pulling in the software to see whether or not the motor driver is busy. And although you can do this over SPI, because the L6470 actually supports a dedicated busy pin, we simply decided to connect that directly to the microcontroller input. Very, very easy to use. Other than that, not much noticeable here. Our charge pump, our regulating capacitors on our voltage in, and our identical motor driver down beneath it are the only notable aspects. So switching over to layout design, this was a pretty big challenge for me, as this was my first board layout. Actually doing this was a good exercise for my much simpler senior design layout subsequently. So the majority of our power components are handled here in this little sector with our 15 volts in, and then our regulator chip over here, our decoupling capacitor in beads, going up to our PDI port right here. External crystal oscillator you see located up in this upper portion, and our PDI, or sorry, our UART port are these three header pins right here. And like I mentioned earlier, we connected absolutely everything on this microcontroller, or almost everything, up to vias, which ended up being super useful, as we did swap the MISO and MOSI pins around, which was not good, and did not allow us to use the software SPI, and the bitbanger we wrote was not very friendly with FreeRTOS, so we ended up just having to swap those over, and having a little extra vias here was super useful. And then finally, our servo header pins simply located over here. Super simple. On the right side of the board is essentially dedicated to higher voltage, the motor drivers themselves, and you'll see there are a lot of polygons used here. This is because we wanted to decrease the amount of resistance between the power coming in and the power going out to the motors. And basically what we've done is we have a single dedicated terminal block that brings in our 24-volt power, our massive, I need to turn these off, the small and large polarized, large polarized and small non-polarized capacitors that we have across that. And then finally into our 2 individual motor driver boards themselves. And we also, as you can see, use 4 polygons to connect them to the 4 terminals per block that would attach to the poles of the motors. This worked relatively well. I think our biggest issue was that I constantly had with these was that they tend to be relatively fragile. I think I killed one by accidentally discharging the charge pump into it or something, and then I killed another by accidentally connecting VCC to the wrong pin. I think in total I had killed like 5 of them by the time we had this final working project, which was kind of sad, but a very good lesson in to be very, very careful with your components. And I am quite happy with how much they ended up simplifying the program, as we didn't have to write any sort of dedicated control system like PID or PD or whatever we would have used, and no encoders necessary as well. So one question that I frequently got asked is, how intelligent is it? Well, the answer is, depends on what you mean. The MinMax algorithm, hypothetically speaking, will never allow the robot to lose a game, because it can see infinitely, well, in this case, a maximum of 9 moves in the future. It will never choose something that will allow it to lose. However, as demonstrated, it is easy to tie the robot, create a cats game, if you play correctly, which is not difficult to do on a game of tic-tac-toe. That being said, it is extremely dumb in other ways, such as if you are the human, per se. So say that I put an O down here. Let's have the robot make its move. Row 2, column 2. Okay, move is made. It tells me to place the move now. I'm just going to be a cheap shot and place multiple moves. It immediately identifies that there are 3 in a row, and it gives me the victory without a second thought. Now, this should be relatively trivial to fix. There just wasn't enough time during the semester in order to do so. However, it would be kind of funny if there was a way to make the robot acknowledge that you cheated and force you to undo the moves that you did wrongly before it would move on. Of course, there are other ways to mess with the robot. Say that you could just go O everywhere. It doesn't have a way of computing whether or not there are too many plays on the board. So if there are 2 X's, like, I could put an X down here, and it would classify that as being something that it wrote. Actually, I need to start a new one for that. But it doesn't have any of the other sorts of intelligence that even a 2 or 3-year-old would have when playing this game. So, can it play smarter than a small child? Perhaps. But does it actually play any smarter? Is absolutely no.